Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. Enthalpy change. For a lesson overview, we're going to first of all look at some enthalpy change, enthalpy diagram profiles. We're then going to move on to defining particular enthalpy changes, and these definitions must be known. We're going to look at measuring enthalpy changes experimentally and interpreting data. Then we're going to use bond enthalpy data to calculate enthalpy change. And then finally, we're going to look at Hess's law, which is a theoretical and indirect method for determining a particular enthalpy change. Enthalpy change is given the symbol delta H, delta for change, H for enthalpy, and it's a measure of the energy change or energy transfer from a chemical system to the surroundings or from the surroundings to a chemical system that results from a chemical reaction. So that energy transfer is of course reversible. The energy is held in the chemical system, it's best to think of, as the potential energy in the chemical bonds. The energy in the surroundings is best thought of as being heat energy. So what I'd like you to do is to use your recall of pre-A-level chemistry and decide for an exothermic reaction. What is the direction of energy transfer? What is the sign for the enthalpy change by convention, delta H? And what is the temperature change of the surroundings that results from an exothermic change? Then do the same for endothermic. Pause the lesson, think it through, write down your thoughts, resume and check your answers. So here is the direction of change. It's to the energy transfer, it's to the surroundings. So in an exothermic reaction, energy is passed and transferred from the chemical system to the surroundings. The opposite is true for endothermic. There, energy is transferred from the surroundings to the chemical system. By convention, the exothermic reaction, the enthalpy change delta H is given a negative sign. And by convention, delta H is positive for endothermic change. Now, if energy is transferred to the surroundings and that energy is stored as heat energy, then the temperature of the surroundings increases. For an endothermic change, energy is transferred from the surroundings and into the chemical system where it's stored as potential energy. So therefore, there's a decrease in the temperature of the surroundings. You are expected to produce enthalpy profile diagrams. So let's do this by example. If I share this enthalpy profile diagram, can you decide whether it is for an exothermic or an endothermic reaction? Pause and decide. So the reaction is for an exothermic change, and we have reactants of higher energy than products. The difference between the two is delta H, the enthalpy change. And for a reaction which transfers energy to the surroundings, the sign for the enthalpy change is negative. If that is for an exothermic reaction, can you draw the enthalpy profile diagram for an endothermic reaction. Pause, complete that task. So here is the enthalpy profile diagram for endothermic. The reactants have less energy than the products. That is, energy has been transferred from the surroundings to the chemical system. So that means the change in enthalpy, delta H, is positive. So the difference between the enthalpy of the reactants and the enthalpy of the reactants and the enthalpy of the products, delta H is positive for an endothermic reaction. It's convenient at this point to remind you of the concept of activation energy, assuming that you've met it in rate of reaction chemistry. Given the symbol EA, capital E subscript A, activation energy, it's a minimum energy requirement for the colliding particles to react. Particles with less than the activation energy on collision will not react. Particles with or with greater than the activation energy on collision will react. So let's look at where we might put that into an enthalpy diagram profile. And we can see here that we've got a classic example for an exothermic reaction. And where would the activation energy be placed? So the activation energy EA would of course be the difference between the energy of the reactants and the energy of the same molecules in an activated state. So we have an activated state up here. It's an energy barrier to the reactants forming the products. Of course, delta H does not change. Delta H remains this value here. The enthalpy change on the y-axis. So activation energy for an exothermic reaction will be represented as I have done in my diagram. Could you do the same on the right hand side here, or on your piece of paper I should say, for an endothermic reaction? Pause the video and complete that exercise. Okay, so looking at this, we see that the enthalpy for change for an endothermic reaction still has an activation energy that is the difference between the reactants and the top of the activation energy barrier, or the activation energy curve. So what might be referred to as the activated state up here. Delta H, I'll just complete all possible misunderstandings. So delta H remains the same, unaffected by the inclusion of an activation energy curve. Moving on to defining particular enthalpy changes, these definitions have to be known precisely. For enthalpy changes to be useful between different chemists, then we need to standardize conditions and states. That's because factors such as temperature will affect the enthalpy change value. For a standard enthalpy change, we have a new sign, delta H, we know for enthalpy change, but then a superscript, either a 0 or a plimsoll line, as you can see in blue there. So that is the standard enthalpy change. So the factors that need to be standardized are concentration, temperature, and pressure. Now, I wonder if you could write down, pause the lesson and write down what you think would be the standard concentration, the standard temperature in 2 units, Celsius and Kelvin, please, and the standard pressure, atmospheres and in kilopascals. Come back to check your answers when you are ready. So the standard concentration is, of course, in moles per decimeter cubed, in other words, moles per litre. The temperature, 25 Celsius. Now, if you're not sure about that, what that converts to into Kelvin, have another go. 25 Celsius, what is that in Kelvin? So in Kelvin you add 273. So in blue I've marked Kelvin because that is the temperature that will be used in chemistry textbooks and in questions. Then in pressure, of course, we have 1 atmosphere. What is that in kilopascals? You either know or you don't. It's about 100 kilopascals. Now, under those conditions, all substances have a state, of course. That state under those conditions is called the standard state and would be indicated as such in equations, reaction equations. So let's look at some particular enthalpy changes. The basic enthalpy change definition is the reaction enthalpy change of reaction delta RH. Now that would refer to a reaction equation, the enthalpy change associated with the reaction equation, but for the numbers of moles as stated in the reaction. Exactly how that pans out you will see when we do some examples, but there are then particular types of reaction that have a particular enthalpy change. The first one you need to know about is the enthalpy change of combustion, delta CH, and this refers to the complete combustion of 1 mole of substance. Following that is the enthalpy change of formation, delta FH. Now this is the enthalpy change for the formation of 1 mole of substance, but from its elements in their standard states. And then the fourth enthalpy change which you are to know is enthalpy change of neutralization, delta newt H, a bit clumsy, but that's the way it's presented. So this is for the neutralization of an amount of acid or alkali to form 1 mole of water. So it's a per mole of water enthalpy change. Now the second, third and fourth enthalpy changes are superior to the enthalpy of reaction. So if you are asked to identify the type of enthalpy change taking place, if it's an enthalpy of combustion, you would call it that rather than an enthalpy of change of reaction. So let's look at some examples on the next slide. So let's do a few examples. I'd like you to try and identify the enthalpy change from the 4 that you've met for each chemical reaction equation. So which description, which label best matches carbon plus half oxygen goes to CO, carbon monoxide. Pause the lesson, come back when you have made your decision. Okay, so let's have a look at this. Well, we've got 1 mole of carbon monoxide being formed. So that would imply that we're making 1 mole of carbon monoxide from the elements, carbon as a solid and oxygen as a gas, from the elements in their standard states. So that is enthalpy change of formation. Why is it not enthalpy change of combustion? Well, because the complete combustion of carbon has not been fulfilled. The complete combustion of carbon would not produce carbon monoxide, it would produce carbon dioxide. So the enthalpy change of combustion criteria are not satisfied. Okay, so try the remaining 5. Come back when you are ready to correct your answers. So let's have a look at this second example. We've got 1 mole of compound. These are elements, carbon and chlorine in their standard states. So we're forming 1 mole of substance 1 mole of compound from the elements in their standard states, so that's delta FH, enthalpy change of formation. Moving on to the third. Here we've got 2 carbons forming 2 moles of carbon monoxide, so it no longer or does not meet the enthalpy change of formation criteria or conditions. So this is simply an enthalpy change of reaction for the numbers of moles as written in the equation. So 2 moles of carbon forming 2 moles of carbon monoxide. Enthalpy change of reaction. It does not match complete combustion. It does not match enthalpy change of formation criteria. Moving on to the sulfuric acid question, well, we're forming 2 moles of water here. So although it's a neutralization, we're not forming 1 mole of water. So this again would fit enthalpy change of reaction, but not enthalpy of neutralization. However, we could say that it's 2 times the enthalpy of neutralization because we're forming 2 moles of water. Moving on to the 5th, methane and oxygen forming water and carbon dioxide, that is complete combustion, so that would be delta CH, enthalpy of combustion of methane. And here nitric acid and sodium hydroxide, so nitric acid and sodium hydroxide making 1 mole of water, well, that would be enthalpy of neutralization. So let's look at a slightly different type of problem. Write reaction equations to express the following standard enthalpy changes. So can you write an equation that expresses the idea of the enthalpy, standard enthalpy of combustion of ethane, the standard enthalpy of formation of methane, and the standard enthalpy of neutralization of sulfuric acid? Pause the lesson, write your equations. You'll need to refer to the definitions and then resume to correct your answers. So we have for the enthalpy of combustion of ethane 1 mole of ethane reacting with oxygen to completely combust to form 2 moles of carbon dioxide and 3 moles of water. Now, standard enthalpy change, so these must be in their standard states: liquid water, gaseous carbon dioxide, gaseous oxygen, and gaseous ethane. Now, we just need to balance for oxygen. We've got 4 oxygens associated with carbon dioxide and 3 oxygens associated with water, so that's 7 oxygens. So we write 7 over 2 O2, so 7 over 2 times O2 gives us 7 oxygens. Why don't I multiply through by 2? Because the definition involves 1 mole of ethane. So there is the correct equation that expresses the idea of the enthalpy of combustion of ethane. Okay, so looking at the enthalpy of formation of methane, well, on this occasion we need to make 1 mole of methane in standard conditions, standard state. So we need to start with the elements in their standard states. Simple balancing. There is no chance of carbon and hydrogen reacting in that way to make methane. That is not the point. The point is that that equation matches the definition of the enthalpy of formation, or the standard enthalpy of formation of methane. And then finally, enthalpy of neutralization of sulfuric acid. Okay, so here's sulfuric acid, but the definition is by moles of water. So we want to form 1 mole of water. So let's react it with sodium hydroxide. But to achieve 1 mole of water, we also got sodium sulfate being formed. To form 1 mole of water, we need half a mole of sulfuric acid. So that will only form to balance half a mole of sodium sulfate. This takes place in aqueous solution. Water is a liquid. So there are our equations that express those enthalpy change values. Moving on, how do you determine an enthalpy change experimentally? Before calculating delta H, the enthalpy change, we need to know what is the energy transfer. How many joules of energy have been transferred either to or from the surroundings. So we achieve that by arranging it so that a chemical reaction transfers its heat into a known mass of substance of known specific heat capacity for which we can measure the temperature change that results. So we then put in to the formula Q equals mc delta T, for which we thank physics. Q, the energy transferred, m, the mass of the substance which has its temperature changed, C, the ability of that substance to have its temperature change, called the specific heat capacity, and delta T, the change in temperature. So let's look at an example, very simple. What if you were to heat a copper block with a match and measure the temperature change? Well, we would need to know the mass of the block of copper, 50 grams. We would need to look up in a data book the specific heat capacity, 0.385 joules per gram, or it will be kilojoules per kilogram. It's the same value. And if I tell you, or imagine that there's a temperature increase of 15 degrees Celsius, could you calculate the heat energy transferred Q? Pause the lesson, carry out that calculation, come back and check your answer. So, very simply, Q is equal to 50, which of course is the mass of the copper block. So the mass of the copper block here, 50, so M is 50. The specific heat capacity, I've quoted at 0.385, put that in the line, and the temperature change, the difference between the initial and the final temperature, is 15. Multiply those together, you get 288.75 joules. Notice, if you put in grams, 50 grams rather than kilograms, 50 grams, then the answer comes out in joules, which you can then convert to kilojoules by dividing by 1000. So let's look at calculating enthalpy change of reactions in solution. So a typical reaction would be when 25 centimeters cubed of 1 mole per decimeter cubed hydrochloric acid is added to 30 centimeters cubed of sodium hydroxide of the same concentration in a polystyrene cup. So we use a polystyrene cup to reduce heat losses to the surroundings, and we can measure the solutions either in a measuring cylinder or in a volumetric pipette, the volumetric pipette being more accurate, of course, by taking the initial and final temperatures, or rather the initial and maximum temperatures, monitoring the temperature change over several minutes, we can determine the temperature rise or change. In this case, I've suggested there's a temperature rise. From that data, we can calculate delta H for the reaction, the standard enthalpy change for the reaction, but we need to make a couple of assumptions. The first one being that the solutions in the polystyrene cup have the same density as of water at 1 gram per centimeter cubed. So that means that 25 centimeters cubed and 30 centimeters cubed gives us a mass of 55 grams of solution in the polystyrene cup. If we assume that the solutions have a density that is the same as water, then we can also pair that with the assumption that the specific heat capacity of the solutions is the same as that of water, 4.18 grams 4.18 joules per gram per Kelvin. From that data, we can then calculate Q, the heat transfer from the reaction into the surroundings, that is the solution or the water holding the chemicals together. So could you pause the lesson and calculate Q? So I'm going to say Q is equal to MC delta T. That's equal to 55 if I keep in grams, times 4.18 times 6.2. That comes to 1425.35 joules. As we started in grams, I'm ending in joules. Now, delta H is a molar quantity, so we have to divide the energy transferred by N, the numbers of moles. Now, where am I going to get the numbers of reacting moles from? Well, I'm going to look at the data here and say the numbers of moles of hydrochloric acid were 0.025, whereas the moles of sodium hydroxide, volume times concentration, 0.30 moles. So the moles of hydrochloric acid are the limiting reagent. So the moles of hydrochloric acid are the limiting reagent. If you need to review that, look at some earlier lessons. So the numbers of moles reacting are the numbers of moles of hydrochloric acid. So to express delta H, I divide 1425.35 by the numbers of moles, 0.025. That comes out as 57015 joules per mole. Now there's two things that can be done to that. Of course, the first thing is we convert it into kilojoules per mole. And I'm sticking to two significant figures because my data is 2 sig fig, 2 sig fig, 2 sig fig. So I'm sticking to two significant figures in my answer, but I also need to assign positive or negative in front of the delta H value. As it is an exothermic reaction, the temperature rises, then we say delta H is negative. So that process, using the two assumptions to calculate Q, dividing by the numbers of reacting moles, which may or may not involve a limiting reagent, and then converting that answer into kilojoules and assigning positive or negative to the value based on whether it's exothermic or endothermic, is the standard process and is repeated in all circumstances involving reactions in a solution. So now I'd like you to try this problem. So calculate the enthalpy change for the reaction between zinc and copper sulfate in solution. So we've got standard procedure, polystyrene cup, zinc powder added to 50 centimeters cubed of 1 mole per decimeter cubed copper sulfate. We have an excess of zinc powder and the temperature changes by 36.2 Celsius. We need to make the same two assumptions as previously, that the density of water is the same as the density of the solutions and that the specific heat capacity of the solutions is the same as that of water. So our framework for the calculation would be to calculate Q, work out the numbers of moles that are reacting, and then calculate the enthalpy change delta H. Pause the lesson and complete that calculation. Come back to check your answer. So Q is going to be 50 times 4.18 times 36.2. So that's going to come out as 7565.8 joules. So I've used grams, so my energy change is in joules. The numbers of moles, well, that's going to be based on the moles of copper sulfate solution. So we do the numbers of moles is going to be the concentration times the volume. So the numbers of moles is 50 over 1000 times 1, that's 0.05 moles. So delta H will be 7565.8 divided by 0.05. That comes out as 151,316 joules per mole. Convert that to kilojoules, 151 kilojoules per mole. I'm going to stick to 3 significant figures because in this example I've got 3 significant figures on the volume. I'm still going to stick with 3 significant figures. You may object. 36.2, 3 sig figs for the temperature and for the density, etc. But I need to add a sign to the enthalpy change value. So we've got a rise in temperature, so that is exothermic, and we give that a negative sign. So one problem that arises in enthalpy calculations is what is the actual true maximum temperature? Because, for example, if we did mix zinc powder in copper sulfate solution, whilst the reaction was going on, it is not an instantaneous reaction, it requires mixing, energy will be transferred in the form of heat to the surroundings beyond the polystyrene cup. And therefore the true maximum temperature will never be reached in the solution itself. However, if we look at a typical plot for monitoring the temperature change for that reaction, you'll see that a couple of minutes are spent establishing a baseline temperature. Then the zinc is added and we see there's a rise in temperature, and that temperature rise is then followed by a temperature fall. Now that temperature fall is associated with the heat losses to the surroundings. So this temperature here is not the true maximum. So that temperature change from the baseline to there does not reflect the true maximum, because during these minutes here heat is being lost to the surroundings outside of the polystyrene cup. So how do we obtain a better estimate of the maximum temperature? Well, we extrapolate from what's called the cooling curve. So we assume that that rate of cooling carries on during the first few minutes of the reaction. So the true maximum temperature is actually up here, and therefore the maximum temperature change is the difference between the baseline figure and that extrapolated cooling curve. So that would be delta T, rather than this value here, which is not the true maximum or the best estimate of the true maximum. So that method is expected to be known and often comes up in examination questions. So let's have a look at the experimental setup for determining an enthalpy of combustion. So typically we would put the organic fuel such as propane or ethanol into what's called a spirit lamp, and we would place that beneath a copper can of water, or it could be a beaker. A copper can, because it's a better heat conductor, is the superior apparatus between those two choices. We put water into the copper can and we measure the temperature change of the water using a thermometer. Now we have a lamp cap to extinguish the flame and also to prevent the evaporation of organic fuels. So organic fuels are pretty volatile, so if you leave them open to the air they will evaporate. There would be a mass change in the spirit lamp without the lamp cap. Then we have an electronic balance. I've got it to 2 decimal places, probably accurate enough for precise enough for this particular experiment. So what I'd like you to think about is, what are the 4 necessary measurements that are needed to obtain data from which the enthalpy of combustion of the organic fuel can be calculated? And what are the 3 principal sources of error? Pause the lesson, think carefully about the necessary measurements and the principal sources. I recommend strongly that you write down your ideas and come back to check against my suggestions when you are ready. So my suggestions for the 4 necessary measurements will, of course, you need the mass of the spirit lamp and the cap before combustion. If you're going to keep the cap on the spirit lamp to prevent evaporation, then you need to have its mass measured as part of the initial apparatus. Obviously you then combust the organic fuel, so you need the mass of the spirit lamp and cap after combustion. You need to know the exact volume or mass of water in the copper can. You can use volume and then assume that it has a density of 1 gram per centimeter cubed, or you can use a balance to measure the actual mass. And then of course you need the initial and final temperatures of the water in the copper can. So you're going to combust the fuel. You need to know the mass of the fuel that has combusted by comparing 1 and 2. You need to know the mass of the water and what its temperature change is. So the 3 principal sources of error are obviously heat loss to the surroundings other than the copper can, and the water in the copper can, I should say. So heat loss to the surroundings, the air that is surrounding the apparatus. The organic fuel may not combust completely, so there may be some soot or carbon monoxide in complete combustion. That will lead to less heat being released. And also, you may not be successful in your efforts, or the experimenter's efforts, to eliminate evaporation of the fuel from the spirit lamp. So those are the 3 principal sources of error. So assuming that the experiment is carried out properly, if you move to the next slide, there is some so let's have a go at interpreting the sort of data that you get from the experiment described on the previous slide. So a spirit burner containing ethanol, an organic fuel. We have its initial mass, weighed 195.6 grams. It's combusted below 200 grams of water, and after combustion it weighed 194.5 grams. The temperature of the water rose by 39.1 Celsius. So exactly the same plan for the calculation. Calculate Q, calculate the moles of fuel combusted, and calculate the enthalpy of combustion of ethanol. Pause the video, have a go at those calculations, come back to correct your answers when you are ready. So we've got Q equals MC Q equals mc delta T, of course. So in this case, we've got 200 grams, which I'm going to keep in kilograms, so that's 0.2 kilograms of water, times 4.18, which is the specific heat capacity of water, and the temperature change is 39.1. Multiply that all together, it comes to 32.69 kilojoules. Okay, because I put my mass into kilograms, the unit of energy comes out as kilojoules. Now the moles of fuel combusted, well, that's the difference between these two figures, 195.6 to 194.5. So that's 1.1 grams of ethanol, which we divide by 46, which is the molar mass of ethanol, and that comes out as 0.02391 moles. So delta H is a molar quantity, so delta H is going to be, if you remember, Q divided by N, so 32.69 divided by 0.02391, it's going to come out as 1367 kilojoules per mole. I just need to assign plus or minus as there was a temperature rise. The reaction is exothermic, so minus 1367 kilojoules per mole to 4 significant figures. So we've covered on this lesson enthalpy change, particular enthalpy changes, and experimentally obtaining enthalpy changes. We're now ready to move on to calculation using bond enthalpy data. You'll find that, as you will find the Hess's law chemistry, in separate lessons. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you. But those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.